out of France came from Olivier Faugerat's group and others, was the application of projective geometry to computer vision. And it really revolutionized some of the work that was gone in terms of how people thought about stereo and other types of relationship between views. What we're going to do is we're going to use this a little bit in our next two lectures where we talk about what's called the essential matrix and the fundamental matrix. Those are a little more intense, so hang on. Welcome back to Introduction to Computer Vision. I'm Aaron Bobick still, by the way. Normally when I've introduced something, I'd say who I am, but I guess you know. Okay. So last time we talked about projective geometry and sort of this relationship between lines, points, and planes, and using sort of the projective relation and homogeneous coordinates as an easy way to describe these things. Today we'll use this a little bit to talk about the relation between two calibrated cameras. Next time will be uncalibrated. Just to contextualize it again a little bit, we have these projective transforms that are these matrices. These are 3D matrices, 3x3 matrices that operate in 2 dimensions that can transform an image in a variety of ways. For 3D, we talked about it being 4x4. We also talked about transformation they're called homographies that would map between planes. This is going to become very important, not in this lesson, but the next one, because we're going to be talking about recovering homographies that map between image planes. We also introduced projective lines, and we talked about that a line in an image plane was just the intersection of the image plane and a plane through the center of projection. That plane would be defined by a normal L, and that's why both a line and a point are 3 vectors in this homogeneous or projective space. And we showed some really cool things. We showed how the equation of a line is represented by the normal components in this projective space. And then a little bit of some cool operations that if I gave you 2 points defined in terms of projective coordinates, you could find the line that connected them by doing the cross product. Likewise, if I gave you 2 lines, you could find the point of intersection by doing their cross product. And these are some tools that we're going to make use of going forward. So let me motivate the problem. Remember stereo? Twice? Good. All right. So if you have 2 views of the scene, and these are 2 cameras that are not necessarily going to have parallel image planes, just 2 views, what is the relationship between the location of a scene point in one camera and its location in the other camera? That was what we wanted to know. We wanted to know if we could know something about that relationship so that we went looking for the matches, we could use it as a constraint. Just to animate it a little bit, if we have a pair of points. So the idea is we have a point P out there in the scene. That point images to some location in the left image plane, center of projection 1 here, and that line maps to a line in the center of projection number 2, and that was what was referred to as an epipolar line with respect to that point. So if you're looking for that point, it's going to have to be somehow on that line. Likewise, the ray from the other center of projection maps to the corresponding epipolar line in the other image, its center of projection. And those pair of epipolar lines, we showed before that they're defined by a plane called the epipolar plane. And that plane is defined, well, the simplest way of thinking about it is that it's defined by this baseline vector, so the translational vector between the 2 centers of projection and this world point. Or you can think of it as being defined by the 3 points, P, CP2, CP1, that's the epipolar plane. So we have a different epipolar plane for each point out in the world. We then talked about what we call the epipolar constraint, right? The idea was if I know about my epipolar lines or I know about the epipolar planes, the epipolar constraint means that if I have a point P in the image on the left-hand side, there's only a one-dimensional search in the right-hand image to look along. That was the epipolar line. For the parallel image planes, everything lined up, it was the same horizontal line. But in general, if I have verged cameras, we show your epipolar lines weren't going to be parallel. And here was this example where we had converged cameras and corresponding epipolar lines. It also allowed us to define a couple of terms. So the baseline was just the vector separating the 2 centers of projection. The epipolar plane we just talked about, given a world point, and that baseline defines the plane. The epipolar lines were the intersection of the epipolar plane and each of the image planes. So that's a pair of corresponding epipolar lines. The epipole of each image was the point in the image plane that intersected the baseline. And we said sometimes you don't actually see that. In fact, if we if we go back to this pair of images here, all of these would have intersected over here. So if this image had been huge, you would have been able to see the epipole, but because it's in some sense cropped out, you can't always see the epipole. The problem with everything that I just showed you is it would be very difficult to turn it into code. Why do I mean that? What I mean is I've been showing you everything in terms of geometry, right? I'm like waving my hands and we got points, etc., whatever. Computers don't do so well with waving hands, and despite what my undergraduates say, okay? What we need to do is we need to go from the geometry to algebra. Because believe it or not, computers are fine for algebra as long as you know what you're doing. That is, you can convert algebraic expressions into computations. In fact, we talked about that earlier. But it's very hard to go from geometry to computation. And the way we're going to do that is we're going to take the geometry and then convert that to algebra. So we're going to start off today with a pair of calibrated cameras. Okay, so here's my pair of calibrated cameras. I have two camera centers, OC and OC prime, and they're both looking at some world point X. And it's viewed in the two images, and it's seen here. Because these are calibrated cameras, I'm going to assume that I know the translation t along the baseline. The t is the vector that is the baseline, right? So if I have to shift, 2, 7, 9 to get from one camera to the other in x, y, z, that's what my translation would be. And I also know r. I know the rotation matrix that you would have to rotate one camera center to become aligned with the other camera center. That's what it means to be calibrated. So we write this way. Okay, it says from geometry to algebra. We're not quite there, but we're almost there. But basically what we're saying is the location of the point x in the prime frame can be expressed by rotating x as appearing in the non-prime frame and then translating it by t. Right? That's just the equations we had before. I know this is not the homogeneous version. That's okay. In a minute we'll make everything beautiful. Before we make everything beautiful, a couple of reminders. Actually, this is the first reminder. Or an aside, I should say, and it's about cross product. The second one's about cross product too. So the first one is to remember that a cross product, so A cross B, gives you a new vector C. And that vector C has the property of being perpendicular to both A and B. So it's in the direction that's perpendicular, and you may also remember that the magnitude of that vector is equal to the sine of the angles between them, which should make you realize right away that if I take any vector A cross itself, that's going to be 0, because the angle between its vector and itself is 0, the sign is 0. So A cross A is 0 no matter what A is. Okay? So A cross B gives you C, C being perpendicular to A and B, and A cross A is equal to 0 no matter what. So here we start our little mathematical foray down into making it from geometry to algebra. So I just wrote what we had before. X prime, the position or location of x in the prime frame, can just be expressed as having rotated the x frame by the r amount and then translating it by t. All right? Great. Let's just cross both sides of that equation by t. So we have t cross x prime on the left, but on the right we have t cross, and it's just because of distributed property, it's t cross rx plus t cross t. All right? And by the way, I wrote here that this is normal to the plane. Remember that t cross x prime is going to be something that's perpendicular to both of them, so that would be perpendicular to the epipolar plane that we're showing here. We'll maybe make use of that in a minute, but I just want you to realize that. More importantly, what you should see is that we've got t cross t here. What's t cross t? Not very much, otherwise known as 0. Okay? So that just means that t cross x prime is equal to t cross rx. Got it? Okay. Now, let's take both sides of that equation, and I'm going to dot it with x prime. So we got x prime dot t cross x prime equals x prime dot t cross rx. I sure hope you're reading this, because listening to me sounds ridiculous. Okay? Well, let's take a look at this left-hand side. Okay? T cross x prime gives us what? Well, it gives us a vector that's perpendicular to the plane containing t and x prime. So it's perpendicular to t and it's perpendicular to x prime. And then I dotted it with x prime. So what am I going to get? 0, right? Because it's perpendicular. And if everything goes well, there it is in yellow. 0 is equal to x prime dot t cross rx. Okay? So far so good? Good. Time for aside number 2. This one's kind of cool, actually. It's more about cross products. So you might remember there's a simple formula for how you can get cross product. You basically do ijk, and then you do a1, b1, c1. You do your first vector, your second vector, and then you do essentially the determinant, and that gave you the vector. Remember that? Remember that? Remember that? Okay, maybe you don't remember that. That was the formula for cross product. If you had been really smart, you would say, you know, I can just write this as a matrix multiplication. Okay? So I just build this little matrix here from my A, okay? And I take my vector B here. And so that says that the first component of C is going to be what? Well, it's going to be minus A3 B2 plus A2 B3. And that is the first component of the cross product of A and B. Same thing for the second component and third component. So we can just write cross product as matrix multiplication. So I'm going to define a little operator, and this little operator is written here. This x, that means cross product, okay? So when I do this little bracket AX cross, that means that I'm going to substitute in this matrix, which is sort of the cross producting matrix of A. So if I wanted to do A cross B, I would just multiply this matrix times B. So the notation, as I wrote here, is A cross B equals, and just this bracket, and here the font is fixed, it's just this bracket AX times B. Something that we're going to make use of, not this lecture, but next lecture, is, and I'll leave, I love it. I used to love it when professors said this. The proof is left to the reader, okay? But you could actually do this. Figure out what the rank of this matrix is. And if you come out with any number other than 2, try again, because the rank of this matrix is 2. Okay, so it's a 3 by 3 matrix, but the rank of the matrix is 2. And we're going to make use of that later because, as you may remember, if you multiply matrices together, ranks can only get smaller. I multiply a rank 2 matrix by some other matrix, I've got a rank 2 situation. Back to where we were. Remember this equation? 0 is equal to x prime dot t cross rx. We just rewrote that again. So now I can get rid of that whole cross product thing, right? And put that cool little funky cross product notation in there, right? Right. All right. So let me do a substitution. I'm going to let E be just this T cross R. Okay, so it's just this substitution in here. Well, as soon as you do that, you realize I have this really beautiful, elegant expression that says x prime transpose E x equals 0. And E is what's called the essential matrix. And what's cool about the essential matrix is that it relates the point x and the same point, but it's described in the other camera frame. And note that these are world points in these frames for these calibrated systems. In a little bit, we'll talk about the relation between the world points and the image points, and it's a little bit closer than you might think because of the projective geometry. In fact, one way of thinking about this real easily is this is equal to 0, right? So what if I multiplied x by some value a? Would the equation still be true? Of course it would. So not only is it true for the point out here, as expressed in this coordinate frame, it's true for every point along that ray expressed in that coordinate frame. Likewise for every point along that ray expressed in that coordinate frame. Ooh, that means it also talks about image points, but we'll get there. All right. One last thing, and this is you're not going to totally get that this time, but that's okay, you're going to get it next time, all right? We said that this works for sort of any point along that ray, and so you can think of that as the homogeneous representation of all the points along that ray. So our E is our 3 by 3 here, times this 3 by 1, so this is another vector here, all right? We'll just call that L, okay? Why am I calling it L? What does L stand for? Well, in some weird language, it said it stood for point, but in our language, it stands for line. So remember that X transpose L, or P transpose L, or L transpose P was the definition of a line in projective geometry. So what this means is if I knew where some point was in the image, so I know what ray it's along in the image, so I know where it is in the image, I could put that point into this equation, and I would have this L, which defines for me a line in the other frame. Just x prime transpose L equals 0. That was the definition of a line in our projective geometry.